Hi there, I'm Tyler Josephson. I've been at the University of Minnesota for the last 3 years as a postdoc in the Siepmann group, where I've used Monte Carlo simulations and machine learning to look at adsorption and phase equilibria in a variety of systems. Since August, I've been an assistant professor at the University of Maryland, Baltimore County, where I'm starting up a new research group, the Atoms Lab, AI and Theory-Oriented Molecular Science. I'm looking for new students and new collaborations, so please reach out on social media or by email if you're interested in connecting. The work I'm presenting today is from my postdoc at Minnesota. The Tzapatsis group, Siepmann group, Dautitas group, and ExxonMobil have been collaborating to engineer and design zeolite nanosheet membranes for separating mixtures of aromatics. We're interested in this because p-xylene is a huge business. It's the main component in the #1 type of plastic, the PET, plastic bottles. And p-xylene is made from a mixture of benzene, toluene, ethylbenzene, and xylene components. And separating especially these 3 xylenes is challenging because p-xylene, ortho, and meta-xylene have very similar boiling points. That makes it a very energy-intensive process. Our goal is to exploit a membrane that selectively passes p-xylene through and stops ortho and meta-xylene from passing through. That way you can have a reactor here. This is a catalyst bed in the green, and you can have your chemical reaction happening here to isomerize the xylenes, and only p-xylene, the desirable product, comes through the membrane. So even though these will reach maybe about 1/3 each at equilibrium, you can selectively produce p-xylene by combining the reaction and separation process. For this, we need a membrane that's stable at high temperature and high pressures, and that's why we're using a zeolite membrane. For those who are not in this field of research, zeolites are inorganic, microporous materials that are made out of silicon and oxygen, and we make more than 1 million tons of these each year, mainly for catalytic applications in petroleum and ion exchange, for detergents. And their functionality is made possible by these different pores, and these are on the same size and shape of molecules. So the beta zeolite, as defined by this 3-letter code, has a 6 angstrom pore. The MFI zeolite has a 4.7 angstrom pore, and so larger molecules will fit inside this zeolite than in that zeolite. The Tzapatsis group has been making these into membranes, so you can exploit these size and shape selectivity for separations processing. And so what you do for this is you grow a zeolite to have a very high aspect ratio. Okay, so these are very thin sheets of zeolite that are formed in solution, then deposited onto a support, and secondary growth fuses them together so you can make a nice membrane material. I think this is one of my favorite pictures. It shows a transmission electron microscopy image of one of these zeolite nanosheet membranes from different cross sections. So we can see this, the A-axis, the B-axis, and the C-axis shown here. You can actually see and resolve the different pores in this zeolite material, and this is exactly how it's able to separate it. We have these larger pores that allow molecules to pass through. And what really makes them work effectively is p-xylene is able to squeeze through, just barely through those pores. Ortho-xylene has a different cross-section, and so this different branching means it can't fit through those pores easily. And so we observe experimentally these separation factors of 1,000 or higher for these materials, and better than other materials that have been produced. So the primary way to predict transport through a membrane is to use molecular dynamics simulations. That's what my colleague Dr. Evgeny Fedosov, who is now at PNNL, used when he used first principles molecular dynamics to predict the barrier for transporting each of these molecules through the nanosheet. So we have one molecule of these different molecules and compute free energy calculations to see what is the barrier from moving from one intersection to another. And we can see agreement with experiment that we observe these 1,000-fold selectivities that are observed experimentally. One of the challenges, though, with this overall approach is these were all done when the zeolite is basically empty. We ultimately, however, want to drive this up to much higher pressures. We want to operate at the experimental conditions, the high temperatures and high pressures that the catalytic reaction is happening. And in order to do this, we want to be able to predict what is going to be the loading and transport at these high pressure conditions. And we anticipate that this high pressure is going to lead to higher flux, but only so long as the material is empty. If we saturate these pores of this material, this is a highly activated process, and we believe we need to have a clear path for these molecules through this material in order to get transport. So our goal for this is to use molecular simulation to predict the loading in this material across a broad range of pressure, temperature, and composition operating conditions, and then to use machine learning to fit a continuous function so we can integrate this into our process model. So we want to perform Monte Carlo simulations in the Gibbs ensemble. And what we do for this is we have one simulation box for the zeolite and another simulation box for the fluid. And we use Monte Carlo simulations to equilibrate and then sample the important configurations of this system. What we do then, for example, one of these Monte Carlo moves, I would randomly pick, for example, the interbox swap move. This involves picking one of these molecules at random. Then we delete it from this simulation box and try to insert it somewhere into this box. We randomly accept or reject this move based on the change in energy, based on the corrected probability for this, and then we move on to our next Monte Carlo move. So this might be translation or rotation, it might change the volume of our fluid box so we can set the pressure of our system, and so forth. After we collect a large number of configurations of this system, we can analyze them and evaluate, for example, what is the loading in each of these regions, what are the energies of interactions, the thermodynamics of this system. We can learn a lot from Monte Carlo simulations. So I'll remind you our two goals are to predict the loading across a broad range of pressure, temperature, and composition operating conditions, and to use machine learning to fit a continuous function for a process model. So what we do is we set up these simulations where we have a 6-component simulation with a real fluid box and a zeolite nanosheet simulation box with ideal boxes to facilitate molecular transfers between these two. And we measure the fluid density, the pressure, and the loading in the different regions of this system. We're using the TraPPE-BTX force field, and we ultimately simulate more than 1,000 different simulation state points across mixture, temperature, and pressure space. So first, a note about the force field we're using for this system. We simulate our aromatics using the TraPPE-BTX force field, which we developed for this project. This is fairly simple. We take the benzene force field and the ethane force field, and we combine them to form methyl-substituted aromatics, where we use the Lennard-Jones parameters and the geometry by combining these. And we compared TraPPE-UA from 1998 to TraPPE-UA2, our revised version of our force field from 2017, and compared the performance with experimental vapor-liquid coexistence properties. And so we have generally good agreement. We find that TraPPE-UA2 is better than TraPPE-UA, and that all of the xylenes are in reasonable agreement with experiment when we use a single set of parameters for these. So this is the types of data that we get when we actually do the simulations with the zeolite nanosheet membrane. So we have 3 different regions of the zeolite. We have the micropore and the surface, which is an 8 angstrom region at the surface of the zeolite nanosheet, and we also have the mesopore, which is the empty space between periodic images of these zeolite nanosheets. And this is just showing data for one composition and a select temperature. So we looked at 10 temperatures, here's showing 5, and a wide range of pressures. So we can see at low pressure, we have low loading, and as pressure increases, we get more loading in each of these different regions. We can see at higher temperatures, we get reduced loading as it becomes untropically not favorable to have the molecules in the material. They would prefer to be out in the fluid phase. And also we see interesting phenomena like step changes. This is a mesopore condensation that we observe because of the confinement in the mesopore between the different layers of the zeolite nanosheet in these periodic boundaries. We don't just get total loading, we also get compositions. So this is just showing briefly at 2 of these snapshots, we have what is the composition, what is the selectivity of adsorption into these different regions at different conditions. And we can also see that, for example, at low temperatures, we have around 33% of the intersections occupied. We increase the pressure, this saturates them and really fills up this headspace. We get to a very high density in the fluid phase. If we increase the temperature, though, now essentially we have 0 intersections occupied at the previous pressure we were looking at. Well, now if we go to high pressure, we can get high loading, high densities in the fluid phase, while we don't see nearly as many intersections occupied in the zeolite phase. Now, this is great. We can see all this information at the experimental high temperature, high pressure operating conditions. But what we really want is a continuous function. And that's why we go to the neural network to model this loading surface. We have an 8 variable input where we have temperature, 6 pressures, and temperature, pressure, and composition for 6 species. Our output is the pressure in the fluid phase, as well as the total loading, and the mole fraction in each of the different regions of our zeolite. So we have the micropore, the mesopore, the surface, and the fluid for all of these. We also do these transformations. We use 1 over temperature and log of the pressure for these. These are intuitively good transformations to do because they take into account the thermodynamic nature. Other details, we're using the ELU activation function and the soft plus and soft max to constrain our mole fractions to add up to 1. And also, an interesting feature, we can actually guarantee that our total loadings and pressures are going to be positive. That's one neat feature of using the soft plus. This also encourages convergence to Henry's law and the ideal gas law in the limit of 0 pressure. So this is some neat ways to incorporate some of the physics behind this problem, some of the chemistry in the architecture of the neural network that we're using. So how does our neural network perform? You can see here that in general we do quite well. This is the neural network prediction on the y-axis and the simulation results on the x-axis. So in these parity plots, you can see generally we're doing a pretty good job in the test set that we are exploring. We can then use our neural network to, instead of simply drawing straight lines between the data, which I showed you before, now we can actually draw smooth curves, which is the neural network prediction interpolating among this behavior. So you can see these smooth curves as a function of temperature, pressure. We can also now interpolate, though, along composition and anywhere in this space that we can potentially explore. And so this will also give us the loadings in the different regions, the micropore, the mesopore, and the surface. So finally, would like to summarize by highlighting that, yes, we can use molecular simulation to predict BTX adsorption from liquid, vapor, and supercritical mixtures. We can, in the supercritical regime, use a single neural network to correlate the full multi-component adsorption behavior for 6 species across a wide range of pressures and temperatures, but we have not been able to successfully predict all across the phase space, which includes these step changes in the phase change as we go from liquid to vapor at lower temperatures. And we have ongoing work to integrate this neural network into a process model with Jingjun Liu and Prodromos Dautidis, who are building finite element type models to simulate the membrane reactor. This has been an incredibly collaborative effort, with membrane synthesis and testing from the Tsipatsis group, finite element modeling of the membrane reactor in the Dautidis group, molecular simulation and machine learning in the Zeitman group, and process modeling and experiments under reaction conditions by the team at ExxonMobil. We gratefully acknowledge support from the Department of Energy, the National Science Foundation, RAPID, the Minnesota Supercomputing Institute, and Argonne National Lab, which provided most of the computational resources for this work, as well as ExxonMobil. I'd be happy to take any questions.